So we're going to continue with 4.1. And the last thing we talked about was functions being linearly dependent and functions being linearly independent, right? All right. So adding to that, if we have functions, a set of functions that are linearly dependent, then that means that there exists C1 and C2 so that you can somehow linearly combine these functions to cancel out. That's what the definition meant. Okay, so I'm just going to show you kind of a good way to eyeball whether some functions will be dependent or not. Well, solving this equation for, let's say, f1, you're going to move C2, F2 over, and then you're going to divide by C1. Well, what does this mean? This is just, what? Two constants, right? Equal another constant. This basically shows that in order for these functions to be linearly dependent, f1 and f2 are just constant multiples of each other. Okay, so therefore, you can say a set of functions is linearly independent when neither is a multiple of the other. Okay. So that's kind of the background as far as dependence and independence is concerned. Let's do an example. Let's say we have f1 of x equals cosine 2x, and f2 of x equals 4 minus 8 sine squared x. So again, the question is, are these linearly dependent or linearly independent? Okay. If you're not sure, probably a good thing to do would be to get this into a different form. What's the good formula for cosine 2x? Okay, so f1 is the same as 1 minus 2 sine squared x. And you can kind of see it right now, right? Are these multiples of each other? Absolutely. So we could say that f1 and f2 are linearly dependent since, and I'll write it as c1 f1 plus c2 f2 equals 0 when c1 would have to be, if I make c1 negative 4, you guys see that these are going to be opposites, right? And then c2 I would keep as what? Yep. Or you could do, 4, negative 1. As long as you can somehow arrange these to cancel out, then we're all good. Okay? Question?
C1 and F1, that's excluding 0.
Questions? We okay, Nisha or Matt? Okay, another one. Let's say we have f1 of x equals x, f2 of x equals absolute value of x. What do you guys think? Well, if you restrict the domain then, right? As is, so let's make this clear. As is, you got f of x equals x. This is absolute value of x, right? So yeah, as is, there's no way that we're going to combine these to cancel out. But, yes, if you restrict the domain, so not dependent on negative infinity to infinity, but if we restrict the domain to what? Or, yep. So if we restricted the domain to from negative infinity to 0, then now the f of x equals x and f of x equals absolute value of x are just opposites of one another, right? And then from 0 to infinity, it's the exact same function. So, I don't know, if we pick this one, we have c1x plus c2 absolute value of x, which equals c1x minus c2x. And that's going to equal 0 whenever what? So if we're looking in the negative real numbers, absolute value becomes negative x, right? So what choices can we do for C1 or C2? As long as they're the same. Good. So whenever C1 and C2 are equal to one another, we get them to cancel out and equal 0. So they're dependent on a restricted domain, but as a whole, not so much. Okay, does this kind of make sense? All right. Let's move on to Wronskians. This is a criterion for linearly independent functions. Right now, if they're dependent, it's pretty easy to show. If we're convinced they're independent, we don't really have a way to say that they are, except, well, I can't find any constants that would make these dependent, so I'm going to say that they're independent. Okay, this is now going to be a more formal way of saying these functions are independent because, and then here's what it looks like. Okay, so we start by supposing that our functions f1 through f sub n of x have at least n minus 1 derivatives. If the determinant of f1, f2, and so on, f sub n in the first row, and then down we just do the derivatives of each function. if the determinant of this n by n matrix does not equal 0 for at least one point in I, then f1, f2, and so on are linearly independent. This, by the way, that's called the Wronskian. And the notation is simply W of f1 of x, f2 of x, and so on. Okay, so this, if you're showing that you're computing a Wronskian, this would be the shorthand way of saying that you're doing so. And then this is what you would compute, and then you would see whether or not this equals 0 at some point. Okay, and we're going to go ahead and prove this. So why does this actually tell us what it needs to? And the reason I want to do this is because we really haven't done too many proofs by contradiction in here. Okay, so this is a proof by contradiction. Now, I like to expose you guys, if you guys go on and take more math classes like linear algebra or fundamental math. Hi. Or if you get a math minor, because you can and you're only a few courses away, you might do some proof work in your higher level classes. You have direct proofs, contradiction, induction, which I'm pretty sure you did in pre-calc, a whole bunch of little things, and we haven't really done too many of these, so it's nice to see how these work. Okay, so for simplicity, let's suppose we only have two functions. Suppose n equals 2, and the Wronskian of f1 of x and f2 of x does not equal 0 for some point in the interval. And now if we're going to do a contradiction proof, the whole idea here is that if this happens, that this is a linearly independent set, if we're going to prove by contradiction, we're going to assume the opposite. We're going to say that f1 and f2 are linearly dependent. Okay, so we start by assuming that if this condition is met, the opposite is actually true. And what we try to do is somehow, working with this assumption, arrive at some contradiction, which would then imply that they must be linearly independent then. Okay, so here's how we can do this. So now, if they're linearly independent, then that means from the definition that there exists C1 and C2 not equal to 0, such that C1 f1x plus C2 f2x equals 0. And since we assume that we can take as many derivatives as we need to, we're going to go ahead and also take the derivatives of each function. Which kind of creates a little system of equations here. Okay, so now if we look at this system, based on the fact that these are linearly dependent, what do we know about F1 and F2? They're constant multiples of each other. So, and then naturally, when you take their derivatives, right, this equation then should be a constant multiple of first one. Does that make sense? So what happens, think back to quick, easy example. X plus y equals 4. 2x plus 2y equals 8. What happens when you get a system where one equation is a constant multiple of the other? What's that? 0 equals 0, which means what? How many solutions are there? Infinitely many, yeah. Okay. So what we're going to say here is that this system has infinitely many solutions. Now, how good are you guys with matrix theory? Do you guys know Kramer's rule? You knew it at one point? Okay, let's do a little review. Kramer's rule. If we have ax plus by equals c and dx plus ey equals f, Kramer said that you can do 2 by 2 determinants, and here's how I always remember the rule. You take, if you're looking for x, in the numerator, you swap out the x column with the answer column. So instead of AD, we're going to put CF. We leave the y column as is, and then the denominator for both of these is always the determinant of the xy coefficients, A, B, D, E. So then y would be what? We're looking for y, so what do we put in the y column? Just put the answer column, CF. We leave the x column alone, and then we still have A, B, D, E here. Okay, what's the assumption with Kramer's rule? If there's a solution, then what? The determinant cannot equal 0, right? Does this sound familiar? Well, what happens when it does equal 0? If it's 0 over 0, I don't even remember if it's, all I know is that if the denominator is 0, and for this proof, all we need to know is that it's one or the other, right? If the denominator is 0, it's one of those special cases where there's infinitely many solutions, or 0 solutions, okay? So if the determinant does not equal 0, then infinitely many is a possibility. So going back to our current problem, which is here we have this crazy system with functions and derivatives that we know has infinitely many solutions, but in order for that to happen, the determinant cannot equal 0, which means that the Wronskian cannot equal 0. Oh, I'm sorry. Too soon. The determinant does not equal 0. That's not what I meant to say. What did I mean to say? If the system has infinitely many solutions, then what do we know? that the determinant of that denominator is going to be equal to 0. Does that make sense? That's what we just spent time reviewing. Which implies then that the Wronskian of f1 and f2 equals 0, which what? Why is this bad? Which is really good, because this is a contradiction proof, right? Yeah, we said earlier that the Wronskian was not equal to 0, right? This is a contradiction. Okay? Thus, f1, f2 must be linearly independent. And that's the end of the proof. Here's a good corollary that you might find useful. If the Wronskian of f1, I'm sorry, that's not what I meant. If f1, f2, and so on actually just f sub n. So if all the functions that we're interested in are linearly dependent, then the Wronskian of that set will always equal 0 for every x in the interval. Okay, we're not going to prove this one, but good to know. So at this point, here's what you need to be comfortable doing, and we'll do an example, but given a set of functions, you should be able to determine whether they are linearly dependent or linearly independent. If they're linearly dependent and you're convinced that they are, what do you have to do? How have we shown that functions are linearly dependent so far? You find constants that would make them a linear combination equal to 0, right? So if you can do that, that'll show that they're linearly dependent. If you're pretty convinced that they're linearly independent, what do you have to do? Well, that would be hard to do, right? If they're linearly independent, compute the Wronskian, and what should happen? It should not equal 0 for at least one point, right, in that interval. That's enough to prove that they're linearly independent. Okay, so those are the two methods we have. All right? Uh-oh. Scratch paper has two sides used. Oh, here we go. All right. So here's a quick example. Let's say we have two functions, one equal to 2, one equal to x. You guys know enough at this point to say by looking at that what? Are they dependent or independent? Maybe you don't know. Okay. Think of the pictures of the graphs. Does x look anything like 2 when you graph it? They do?
Well, they're both lines.
They are both lines, yes. So here's what they look like, right? Is there any constant that you could somehow attach to these so that they both cancel out? Unless you both make, if you make them both 0, right? We can't do that. Okay, so if you can't see it, think of the picture. You can't really multiply by anything. So maybe this is perfect then. So maybe we don't know. Maybe we're taking an educated guess that these are linearly independent, right? And now we're going to convince ourselves by computing the Wronskian. So we want to find the Wronskian of 2 and x, which in this case is just a 2 by 2 determinant. And the first position is 2. And then filling on down, we just take the derivatives, right? So what's the derivative of 2? And then here we have x. What's the derivative here? 1. What's the determinant? 2 minus 0, which is 2, which never equals 0. Not even for a point. For any point, it never equals 0. Ever. So what does that mean? It means that f1 and f2 are linearly independent. Okay? Yes? It's got to be a square matrix. So if you have 3 functions, just fill out the top row, and then you should take 2 derivatives. So it's always one less. It's always one less than the number of functions you have. Does that make sense? Okay. Good question. Anything else? All right. So we know about existence of unique solutions. We know about Wronskians, linearly dependent, independent functions. Let's go on to the third section. We're not going to finish it. We'll finish it up tomorrow. So the last third is now actually talking about solutions of linear equations of higher order. All right. Let's write 2 things down. Star 1, star 2. Star 1 is going to be a sub n of x. It's the usual linear equation, but we're going to set this one equal to 0. Star 2 going to be exact same thing, but now it will equal, instead of 0, some function g of x. Okay, this little difference between having a 0 and a g of x is going to be huge for us, okay? This first equation here is called homogeneous. And you're probably wondering, but wait a minute, homogeneous meant something else last chapter. My response, yes it did. Now it means this. Homogeneous means that linear equation equals 0, in this case. Bottom one, we're going to say it's non-homogeneous. Okay, obviously this is going to be easier to deal with, and you'll see why in a matter of days. This one involves a little bit more work, but it's completely and entirely based off of what we do here, okay? So here are some basic assumptions that we're going to have moving forward. All coefficients are continuous. G of x is continuous. And a sub n of x does not equal 0 for all x. So we're going to work with the fact that a unique solution exists and we're going to end with this last principle here, quite an important one. It's called superposition. If you had known this principle in Unit 1, one of the problems on the exam would have taken you 2 seconds. You would just say, this is true by superposition, and then move on without showing anything. Here's what it looks like. So let's say we have a set of k solutions to star 1 on some interval I. Meaning that if you plug y1 into star 1, it's all going to work out. If you plug in y2, that all works out. If you plug in y sub k, or any of the ones in between, that is beautiful and it works out perfectly. Then here's what we know. Then I can make another crazy solution called y equals c1 y1. Let's go ahead and put the of x notation. c2 y2 of x, and so on, down to c sub k, y sub k of x. Then this combination of the solutions is also a solution. We'll go ahead and prove this tomorrow. We'll pick up there. I don't know if you remember on an exam, but in Unit 1, I can stop the video now, but in Unit 1, what did we do? We pretty